Power management of PHEVs. A PHEV involves the operating conditions of both CD mode and CS mode. Typically, when the battery is fully charged, the vehicle is operated in CD mode, and when the battery state of charge SOC reaches a low threshold, it switches to the CS mode. In CD mode, the vehicle will maximize the use of battery energy. In CS mode, the vehicle will use gasoline to power the vehicle while maintaining the battery SOC at the same level. During the CD mode operation, the goal of vehicle power management is to minimize the total energy consumption by distributing power between the battery and the gasoline engine or generator for a given driving scenario. In other words, the goal of power management in a PHEV is to minimize the fuel consumption for a given drive scenario. For a series PHEV or EREV, if the drive distance is less than the nominal electric drive range, then it is possible to operate the vehicle in all electric mode. Hence, no fuel is consumed. If the drive distance is longer than the electric range, then there are three possible operations for operating the vehicle. First one, operate the vehicle in electric mode until the battery is depleted to a present threshold, then run in CS mode. Second one, operate the vehicle in a blended mode with the engine turning on at high power demands and deplete the battery to the preset threshold at the end of the total driving cycle. Third approach, operate the vehicle in a blended mode with the engine turning on at high power demands but with an optimal battery discharge policy. So the battery will be depleted to the preset threshold before the end of the total driving cycle. In these approaches, since the total drive distance is the same, the one that consumes the least fuel will be the best choice. The fact that the battery will exhibit a larger power loss at high power output in comparison with to its output power, it may be advantageous to operate the vehicle in blended mode. The optimum problem can be expressed as minimum fuel consumption subject to a distance and drive cycle. For a blended PHEV, since there is no pure electric range available, the goal of the power management is to minimize fuel consumption for a given drive cycle and given total battery energy available. This is strongly related to the characteristics of the power sources, battery and engine. This slide shows an ideal blended PHEV model for studying power management. In this model, the mechanical coupling and transmission losses are considered as part of the calculated vehicle power. The total vehicle power requested to satisfied by adding engine output and motor output. In this equation, P naught equal to Pm plus Peng and Pb equal to Pm plus Pb plus Pm, where low power case small p represents losses and uppercase capital P represents total power or output power. The vehicle power demand can be calculated using the driving cycle profile. This slide shows the distribution of vehicle power demand, and in this the normalized power demand of vehicle where function f p naught represents the total time that the vehicle spends at a certain power demand p naught. And coming to this, the total battery energy consumed during the drive cycle is EB integral P minimum to P maximum, PB function of F P naught dP naught. The total fuel consumed is FE equal to integral of P minimum to P maximum function P engine function P naught dP naught, where FP engine is the fuel consumption of the engine for a given power output of PENG. The optimization problem is to minimize the total fuel consumption FE for a given battery energy EB equal to constant. End of life battery for electric power grid support. In general, battery energy capacity tends to fade over time and over discharge cycles. Typical battery energy capacity as a function of time is shown in this slide. With 70% SOC depletion, a lithium ion battery can typically last 3000 to 4000 charge cycles. This is approximately 10 years for a PHEV. At that time, the battery capacity may be only 50% of its initial capacity. While this is not satisfactory for the vehicle owner due to the reduced electric driving range, the battery itself may be used for other purposes, such as for grid support. Since there is less space or weight constraints for power grid applications, these batteries can be used for grid energy storage for peak shaving, frequency regulation, and stability control. When more and more renewable energy is connected to the electric power grid, stability of the grid becomes extremely important due to the intermittent nature of renewable energy generation.